we did in the last class, we did electric fields of a short dipole and found the fields for electric field of a short dipole, then far field components of the short dipole. So you have three field components, ER, E theta, H phi, and two far field components, E theta and phi. Then we also did significance of the field components, which is very important. Your ER component is the only the induction field component, and H phi component is the radiation field component. E theta has all the three components. So ER component is will vanish in the far field because induction field will become zero and your radiation field will dominate. So ER component will be negligible in the far field. And just to tell you, last time in microwave antenna, we have received a 100% result, which I was informed yesterday. So I hope that you will carry that legacy and get 100% result. I hope so. Right, Mahima?
Yes, sir.
So Mahima and Purva Chandra, you are the two students I'm expecting S grade. I hope you won't disappoint me. Right? Will you get S grade?
Yes, sir.
What yes, sir? Yes for yes, sir.
S grade, sir. We'll get S grade.
See, these grades will be very important for higher studies. You won't may not be that much important for jobs. See, for example, you want to do masters in antenna related or microwave related subject. So your professors in universities abroad might look at the grades you are scoring in that particular subject of your interest. You got my point?
Yes, sir.
Yes, sir.
And I strongly urge the students to consider doing higher studies because the career opportunities what you have in research and development is really manifold. So if you do higher studies in a good university, either in India or abroad, you will really get so many opportunities for doing many things which you have otherwise not thought of. Again, take down this diagram. This is again diagram of a short electric dipole.
Good morning, Dr. Narayan. I have joined.
Yes, welcome, Wing Commander Raw. So I was a little bit tensed inviting this Major General Dogra. So that is why I was a little late.
Yeah. It's okay. We can handle it. No problem. We'll
No,
do some good.
I will discuss with you after the class.
Yeah, sure. And strength is again very less, 39. In fact, 37.
See, sir, I have, even if there are 20 interested students, I have no problem.
Yeah, correct. That should be the attitude.
I will do my duty. Rest I will leave to the students to follow. So we are doing radiation resistance of short electric dipole. Okay. So this will be a separate question in your VTU examination, and definitely these fields of a short electric dipole, radiation resistance of short dipole will be asked in your internal test because that is the syllabus I have covered. So I have nothing else to ask. So I will be sharing you the syllabus shortly. So anyway, this is one of the questions which is going to be asked. So this is the dipole antenna, and this is the radiation which is happening. Can anybody tell how to get rid of this box which is coming while I'm typing? Something I have done here. Okay. Have you all drawn this diagram?
Yes,
Yes,
sir.
sir.
Okay, fine. This is your radiation. This is your dipole antenna. Okay. Please write down average pointing vector is given by S, that is your average pointing vector of real part of E cross H conjugate. Please write down this. All of you are able to see loud and clear, quite clear. Call this as
Yes, sir.
Yes, sir.
call this as equation number 1. Next, the radial component radial component of the pointing vector is given by radial component of the pointing vector is equal to half of real part of E theta H phi conjugate. Call this as equation number 2. Next, E theta. All these are from field theory, therefore I am not going into depth of it. E theta by H phi is nothing but your Z, which is your intrinsic impedance. Intrinsic impedance. Do you remember this? All this from field theory. Vikram sir has done this. Remember or don't remember? Mahima.
Remember, sir.
Okay. Even if you don't remember, I'm writing it here. No need to worry. E theta is equal to H phi into Z. Okay. Now, okay. Substitute the value of equation 3 in equation 2. Substitute substitute the value of equation 3 in equation 2. Okay, So what happens if I substitute equation 3 instead of E theta, it will be H5 into Z. So your radial component of pointing vector S of R will be half of the real part of H5 complex conjugate. See, H5 into Z I am substituting instead of E theta over here. Can you understand? E theta is H5 into Z that I am substituting in your equation 2. So you will get half of real part of H5 complex conjugate into Z. So call this as equation number 4. So I will get half of what I will get. Half of H5 whole square into real part of Z. This is your radial component of pointing vector, or it can also be written as half of modulus value of H5 square. What is real part? This Z can be written as intrinsic impedance of free space is nothing but square root of mu naught by epsilon naught. This is your final equation for your radial component of pointing vector. Okay. Next, please write down to find. Till here, any doubts?
No doubt, sir.
Next. To find the power radiated and non power radiated is double integral of radial component of point vector into surface integral ds into surface integral ds. So what is your S of R? So this will be your power radiated is equal to half of this S of R. I am substituting from the above equation. So mu naught by epsilon naught will come outside the integration bracket. So what is the integration limit? Do you remember? 5 varying from 0 to 5 varying from 0 to Mahima.
So 2 pi?
Yes. Who else is there? Let me find out someone here. Rakshit, are you there? Rakshit, are you there? Okay. Bhavana SP, are you there? Okay. What
Yes,
is
sir.
theta limits, ma? 0 to?
Pi.
Excellent. 0 to pi. Then it will be r is your ds will be r square sine theta d theta d phi. Agreed? All of you agree till here?
Yes, sir.
Okay.
Yes, sir.
Somewhere I have left h5 here. Wait, the h5 square I have to write. Okay. Okay. That is the modulus value of h5 square. Now go back to the previous derivation. Now this part you have to remember. What did we do h5 here? J naught j I naught beta L divided by 4 pi r sin theta e raised the power j omega t minus r by c. That is your far field component of h of phi. So for your radiation resistance of short dipole, you have to take the far field component of h of phi modulus value. So modulus value of h of phi, what will happen here? I naught beta L divided by 4 pi r sine of theta. All your imaginary components will go. Am I right?
Yes, sir.
Yes, sir.
So modulus value of h of phi will be equal to I naught beta L divided by 4 pi r sine of theta. This is your modulus value of h of phi. So what I have to substitute there? H of phi square. So what I will do here? H of phi square of h of phi. If I do square of h of phi, what I will get is I naught square beta square L square divided by 4 pi whole square r square sine square theta, right?
Yes,
Yes
sir.
or no?
Yes, sir.
So now power radiated will be half of square root of mu by epsilon naught integration phi varying from 0 to 2 pi and your theta varying from 0 to pi. This h of phi will be I naught square beta square L square sine square theta divided by 4 pi square r square into what is the r square d of s surface integral sine theta d theta d phi. Is it clear what I have done? Substitute that value of h of phi. So what will happen here? R square will get cancelled. Yes or no?
Yes, sir.
So what we will get is power radiated will be half mu naught epsilon naught I naught beta square L square divided by 4 pi whole square. Okay, integration of phi varying from 0 to pi and theta varying from 0 to pi sine cube theta d theta d phi. Yes or no?
Yes, sir.
Okay. So if I have to write this, I'll rewrite as half of square root of mu naught epsilon naught I square beta square L square divided by 4 pi square theta varying from 0 to pi sine cube theta d theta phi varying from 0 to 2 pi d phi. Okay, so this will be half of square root of mu by epsilon naught I square beta square L square divided by 4 pi square. This will be 4 by 3 integration. So this already we have done in the unit 1, unit number 3. So I want to do this integration will be 2 pi. Okay. So what will happen here? This will be 2 ones are. This will be 2 twos are. Correct. Then 2 into 2, this is 4. 1 4 will get cancelled here. So this square part will get cancelled with this and this. Agreed? This will be
Yes, sir.
this will be our power radiated. This power radiated is equal to mu naught epsilon naught I naught square beta square L square divided by 4 threes are 12 pi. Call this as equation number 5. Call this as equation number 5. Please write down now. Assuming no losses, the power stream coming out of a sphere is equal to power delivered to the dipole. Okay. This power represented in equation number 5 must be equal to the square of RMS current I square RMS flowing on the dipole multiplied by the radiation resistance. Okay. They are multiplied by radiation resistance. Therefore, equation 5 can be equated to the power actually radiated by the dipole. Okay, so your equation 5 is nothing but I naught square beta square L square divided by 12 pi into square root of mu naught by epsilon naught is equal to I naught by root 2 whole square. This is nothing but your I RMS value into radiation resistance. Now you have to find out this radiation resistance. Okay. So if you rearrange and do all that circus, so you will get radiation resistance is equal to beta square L square divided by 6 pi. See root, what happens here? Root 2 square will be 2, 2 goes there, 2 ones are 6, 6 pi. Right, agreed. I naught will get cancelled. Yes or no, Mahima? Are you with me?
Yes, sir.
Into mu naught by epsilon naught. Write down for vacuum. For vacuum, mu naught by epsilon naught. Mu naught by epsilon naught is equal to 120 pi or is equal to 377 ohms, and your radiation resistance will be what? Beta square L square divided by 6 pi into 120 pi. It will be easier for you to solve. So pi will get cancelled. This will be 6 ones are 6 20s are. So your radiation resistance will become 20 beta square L square. This is your value of your radiation resistance. Now you have to further simplify this. So beta I have to substitute as 2 pi by lambda. 2 pi by lambda. So your radiation resistance will become 20 into 2 pi by lambda whole square L square. What will be this? 80 pi square L by lambda whole square. So this is your radiation resistance of a short electrical dipole. This is your final answer for radiation resistance of a short electric dipole. You want me to recap what we have done?
Yes, sir.
You know, there is something known as field theory. Agreed? All of you have studied that.
Yes, sir.
Yes, sir.
Okay. Just a 5-minute story I have to tell before telling the significance of that. Did you ever think where will you apply that field theory? Straight away I did the derivation here. Many would not have understood head and tail of what I have done, except the mathematical sequencing of what I have done. Agreed. Most of you did not understand head, tail, and the or the reason behind what we have done. Agreed.
Yes, sir. Yes, sir. Agreed.
Agreed.
So it looks more like a mathematical class rather than a engineering class for you. Agreed, Wing Commander Rao. I think no one would have understood what I have done right now. Okay. Now,
Yeah. Correct. It is really tough actually. If you lose out 1 second, then you will be in a difficult situation to catch up.
No, there are two aspects to this derivation. One is the mathematical aspect of what I have done. That somehow the students like Mahima and Purvachandra Prakash will find out, and Bhavana will find out and do it. That is not the issue, and most of the students will do it. The reason why I have done what I have done. See, for example, please come back to this figure. This is a dipole antenna, a simple dipole antenna. See, just to display to you what is a dipole antenna, suppose this one wire I take, make it straight here, and one more wire I will make it straight down like this. Are all of you are able to see my screen? Okay.
Yes, sir.
Okay. Just connect these wires to the microwave transmission source. Just connect these wires to a microwave transmission source. Okay. Any high frequency source of megahertz and above you just give, this will start radiating. This will start radiating. Now, the efficiency of radiation of this antenna, please listen very carefully. The efficiency of radiation of this antenna or any antenna for that matter depends on its radiation resistance. Depends on its radiation resistance. Any efficiency of radiation of antenna will depend on its radiation resistance. Agreed?
Yes, sir.
Okay. So, Purvachandra Prakash, please repeat what I have told. Efficiency of radiation of antenna depends on its dash dash.
Radiation.
Radiation what? Radiation resistance.
Yes, sir.
Okay, fine. So, Tanupriya, can you repeat? Efficiency of radiation of antenna depends on its
radiation resistance.
excellent. So, Mahima, please tell me, radiation resistance should be high or low? Suppose you are the antenna design engineer for some antenna for telescopic applications or inter-space applications or defense applications. Suppose tomorrow you get selected in DRDO, you write GATE. You get selected in Aeronautical Development Establishment. Okay, ADE. Have you gone to the ADE campus?
No, sir.
Okay, so it is worth visiting that. The kind of work they do, we have to salute those scientists. Okay, see, a long time back when I was doing MTech, I was looking for project. Our project is 1 year project. So I went to the Dipole campus along with my father. He's an army officer. So he gets a lot of respect, all salute and all. Straight away, I was taken to the director's room of ADE. Then he told, you better do it in Dipole, that is Defense Bioengineering Electromedical Laboratory, because my MTech was in biomedical engineering, and ADE scientists were very, sincerely working towards the radar development for Air Force applications, for defense applications, for missile systems.
Can we take them, Dr. Naran? Can we take them for the visit? AD and LRD or Air Force Station?
Yes, sir. We have to take them. See, let me finish my experience. So, okay, the way the scientists were working, they were almost working 15 to 16 hours a day that time. We were thinking government officials never work. That is the general mindset. You know, being an young person that time, I saluted them. I told nation requires you more than us. These were the words told by me to them. See, they are working day and night, and this is what they are calculating. Okay, one of the parameters of the design, radiation resistance. Suppose you get selected for ADE, Aeronautical Development Agency, Aeronautical Development Establishment. Both are two different organizations. They have their own sub-roles, which I cannot tell you because these are all national secrets. One works on avionics, one works on aeronautics. So I cannot tell you all those secrets, even though I may know it. So LRD is there. There are so many GTR is there, gas turbine research. Anyway, that is for mechanical engineers. But really, these are all government's, Indian government's assets for scientists. So once I went with my professor, Dr. Srinivas, the kind of welcome we got was really I can still remember that time. That time Raksha Mantri was there, so Professor Srinivas gave a talk, and suddenly I was asked by Professor Srinivas to continue his talk on something on photonic sensors for missile development or something like that. I exactly don't know what I spoke, but I spoke. Okay, that is a different matter. Now, coming back to where I have started, so radiation resistance should be higher or less?
Sir, to increase the efficiency, the radiation resistance has to be decreased, sir.
Yes, excellent. So now all of us agree for any antenna, efficient antenna system to radiate, there is one term known as radiation resistance which required to be designed. While designing the antenna, the radiation resistance should be kept as less as possible. Okay, so these are the things which I'm telling outside the VTU system. Now, suppose you join as a AD scientist and somebody asks you a question about radiation resistance, you should not blink like blinkers. So you should give some proper answers with a loud and commanding voice. Okay, so radiation resistance should be made as less as possible. You can't make it negligible. If you make it negligible, you are super efficient and you will get a Nobel Prize. That I can guarantee you. Okay, so assuming that nobody gets a Nobel Prize and we don't make the radiation resistance zero, so you have to make the radiation resistance as less as possible. Now coming back to something known as field theory, you have studied electromagnetic waves. So what happens here is, still here you have what is known as a circuit theory. Now don't draw what I am drawing now. So this will be connected to a source supply. So you will have the source and the supply coming here, and that is your electrical circuit. Okay, that is your electrical circuit up to the dipole antenna part. Do you agree?
Yes, sir.
Okay. Now there is something here. Wait, I'm trying to delete this. Okay. Okay, done. So there is something here. Once it radiates into free space, is there any electrical circuit?
No, sir.
When it radiates into free space, Tanupriya, please join our very important discussion. When it radiates into free space, is there any electrical circuit?
No, sir.
Okay. Yashika, are you there? Last time when I called your name last class, you weren't there. Or if you are having signal problem, that is a different issue. Okay. Okay, Simran Saxena, are you there? Okay. Shreyas BV, are you there? Okay, most of them seem to have switched off their microphone or whatever is the case. So now what happens? Where was I? Tanupriya, where was I?
So you were discussing about the circuit. Is it present or not?
Yes, in free space, is any electrical circuit present? Can you have a closed wire?
No, sir.
Okay. So since you can't have a closed wire, those kind of equations are described by electromagnetic waves. Now, if I have to find the radiation resistance, I have to equate the electrical circuit radiation power to the electromagnetic power which is in free space. if I have to find the electromagnetic power which is there in free space, I need to use what is known as a Poynting theorem from electromagnetics. Since it is in the radial direction, you will have only the radial component of Poynting vector radiating power, and your theta and phi component will not exist insofar as power is concerned. Okay, assuming it is an isotropic source. Isotropic source with, it means it radiates with equal intensity in all the direction. So in case of isotropic point sources, the component S theta and S phi is 0 because the ratio of the change of the power flow per unit area is 0. So you will have only the SR component of the Poynting vector or the radial component of the Poynting vector. So what I need to do is, I have to equate I square. Sorry. So what I need to do is, I have to equate I square RMS into power radiated. This will be integrated over the radial component of Poynting vector. That is what we have done here. Double integration of radial component of Poynting vector ds. So if you equate these two, you can find this radiation resistance of your short electric dipole. So this is the power radiated due to electric circuit. This is your power radiated from field theory, FTL, right? Or the Poynting vector. So these two you need to equate and find this radiation resistance. So that is why we have done all this exercise. So the power radiated in free space is given by Poynting vector, half of real part of E cross H conjugate. So radial component will be half of real part of E theta H phi conjugate. So E theta by H phi is your Z intrinsic impedance. E theta will be H phi into Z. Substitute the value in equation 2. You will get this component of SR, then integrate over the surface ds, theta varying from 0 to pi, phi varying from 0 to 2 pi. Take the H phi component, modulus of the H phi component for the far field from the previous derivation, then substitute it in the equation. You will get a equation for power radiated. This power radiated equate to the actual power radiated, or the depends on the current input to the antenna. I naught is the maximum value of current, but we should take the root mean square of the current whenever you are considering the current. So you do I square RMS, equate these two, find the radiation resistance, that is 80 pi square L by lambda square. Any doubts? Any doubts? Anything anybody would like to ask?
What will happen to the students who have not attended the class? That is my biggest worry. It is so
You
nice.
have a right question. I do not have a right answer to your question. So I am we can discuss that at the end of the class. So as of now, who are present here, have you understood? See, unless they attend the class, I cannot guarantee that they will understand.
Yeah, that is important.
So these are very important concepts for the examination point of view and your career point of view both. Because all of you are electronics communication engineers and most of you would like to work in electronics communication field. If I am
they have to work somewhere in their, definitely they will have to work. Even if it is in defense or wherever they go.
So whether you go to ADE, whether you go to Indian Air Force, whether you go to Indian Army, or whether you go to private sector, or whether you go to higher studies, you have to work somewhere. Because your age is around 22, assuming you live up to another 50 years. This is the statement I used to give in the offline classes. Your life expectancy is 72, assuming that you don't maintain your health properly. On an average, life expectancy is 70. Without proper exercise, without proper mental and physical exercise, that life expectancy can come down to 50 and 45. You have seen that very often those who have weak immune system and those who do not exercise properly, their life expectancy will drastically come down. We being in defense, although I am not in defense, yeah, now we are inviting one wonderful speaker for this Saturday, General Dogra, a very senior army officer. So those people's life expectancy can be 92, 93 easily, the way they are maintaining their physical health and standard. So assuming that all of you live up to 72, you have to work at least some 30, 40 years with the rate of inflation. So when you have to work, you have to find a career which is stable and which will give you a good career growth. So please think in those lines. It is just not finishing this antenna, writing the exam, vomiting the exam, and be done with that. These are the things I usually tell in my offline classes. And since I'm not able to meet you offline to various reasons, even though the university might permit us to do offline classes, by the time your examination will come. When is your exam starting, Tanupriya? Sorry, Mahima?
So 8th Feb.
8th Feb.
8th Feb, but then you will have lab externals. That will be in January end.
Yes.
Yes, sir.
So there is no time available. So if I do not take class, gone case. See, you had some placement training which was beyond anybody's control, which had come 45 days. So neither I can blame you, neither you can blame me. So we cannot blame each other. So with the best available time, we can do the best available thing. It is like we are reading in war footing right now. We are not in peace time. We are in war time. Actually, there is a saying: more you bleed in peace, less you bleed in war. So right now we are bleeding in war because we have not we have not really given our sweat in peace.
Yeah, I agree with you.
See, although I am a full-fledged civilian, I talk like a defense person because that has really helped me to grow in my life. Whatever I have done, PhD, whatever I have achieved is because of my discipline and sincerity. Any teacher you ask, they will appreciate that I was not a very intelligent person. I was a very hardworking person. Okay, anything you would like to ask? Fine. So if this radiation resistance you have understood, next I will do is quickly I will try to do one more derivation. Please write down radiation resistance of lambda by 2 dipole antenna. Okay, same way you start to find the radiation. Write down, please quickly write. We'll try to finish as fast as possible to find the radiation resistance of lambda by 2 dipole antenna. Find out pointing vector half of real part of E cross H conjugate. Call this as equation 1. See, first few steps are exactly same from the radiation resistance of short dipole and lambda by 2 dipole. Write down, since S theta is equal to S phi is equal to 0. Therefore, SR, radial component of pointing vector, is given by half of real component of E theta into H phi conjugate. This call this as equation number 2. Okay. Then E theta is equal to H phi into Z. So your E theta is nothing but H phi into mu naught by epsilon naught. Okay, call this as 3. Again substitute 3 into Substitute equation 3 in equation 2. So you will get a radial component of Poynting vector as half of real part of h phi square into square root of mu naught epsilon naught. All this as equation 4. Till here the procedure is exactly same. From here your problem starts. Right now next is power radiated is equal to double integration of s of r dfs. That is your this one. So that will be nothing but your theta varying from 0 to pi, your phi varying from 0 to 2 pi, radial component s of r square sin theta d theta d phi. Are you following up to this point? It is exactly same as the previous derivation. Agreed?
Yes, sir.
Okay. So half of Purva Chandra, agreed?
Yes, sir.
Theta varying from 0 to pi, phi varying from 0 to 2 pi. See, I'm able to write quite fast because the previous derivation I worked. That's all. Nothing, there is no magic behind this. So this will be h phi square r square sin theta d theta d phi. Now, here is what the difference will come between the short dipole and the lambda by 2 dipole. H phi, you can't directly substitute this value. I naught beta square, I naught beta L. This is what we substituted. No, I naught beta L divided by 4 pi r sin theta. This is the value of h phi we substituted for a short electric dipole. Agreed?
Yes, sir.
So in this case, the h phi we can't substitute as we substituted for a short electric dipole. For a lambda by 2 dipole, you please write down this value of h phi. So I don't have time to sit and derive this. So you will get this as I naught divided by 2 pi r. Write down very carefully cos of beta L cos theta by 2, cos of beta L cos theta by 2 minus cos of beta L by 2 divided by sin theta. So this is what you are required to substitute as a value for h of phi. This is what you have to substitute in the above equation. So call this as equation number 5. Substitute the value of h of phi in equation number 5. Okay. After you do substitution and all that circus, so in order to save time, I'll just write the equation, final equation. If you want me to derive each step now, or can I go a little faster? Please tell me what I have to do. You want me to do each step? Mahima, I'm asking you.
So no, sir, you can move on to next step, sir.
Okay. No, your next step means I'm going to the final result. So if you want me to do each and every step, I can do. So you have to do square of this. This is a h5, h5 square you have to do and substitute it here. Okay. So I'll quickly tell you what happens if you substitute that. So you will get half of mu naught epsilon naught theta varying from 0 to pi, pi varying from 0 to 2 pi h pi square. So that will be I naught square divided by 2 pi square r square. Agreed. 2 pi square r square. Then this one will be cos of beta L cos theta by 2 minus cos beta L by 2 whole divided by sin theta, this whole square, into r square sin theta d theta d phi. So this r square will get cancelled. This r square will get cancelled with this r square. This will be sin square theta. So this sin theta will get cancelled. So the square will only exist up to here. Agreed. So this will be only sin theta. Agreed.
Yes, sir.
Then few more mess will happen here. So I can rewrite this as half into 120 pi I naught square divided by 2 pi square theta varying from 0 to pi, pi varying from 0 to pi. So what will happen here is this will be cos of beta L cos of theta by 2 minus cos beta L by 2 whole square d theta by sin theta. This will be d phi. Agreed? Agreed.
Yes, sir.
Yes, sir.
So what I will get here, half of 120 pi, this will be 4 pi square I naught theta varying from 0 to pi cos of beta L cos theta by 2 minus cos of beta L by 2 whole square divided by sin theta d theta. So integration of pi varying from 0 to 2 pi d phi. So this part will be 2 pi. So I will get here this 1 pi will get cancelled. So I think this will end up being 15 I naught square by pi. This integration will be 2 pi. This pi will get cancelled. This will be again, this will be 0 to pi integration of cos of beta L cos theta by 2 minus cos of beta L by 2 cos of beta L by 2 square divided by sin theta d theta. So your entire power radiated will be equal to 30 I naught square theta varying from 0 to pi cos of beta L cos of theta by 2 minus cos of beta L by 2 divided sin theta d theta. What is this equation number 6, I think? Now you come up to equation 6, you need to practice that. Okay. Okay. Write down next power power radiated, or sorry, power delivered to the lambda by 2 dipole antenna is equal to P is equal to I square RMS into radiation resistance. So this will be nothing but your I naught by root 2 whole square into radiation resistance. Call this as equation number 7. So you have to equate equation 6 to equation 7. So what will happen is your I naught square by 2 into radiation resistance is equal to 30 I naught square, your theta varying from 0 to pi beta L cos theta by 2 minus cos of beta L by 2, this whole thing whole square d theta by sin theta. I naught will get cancelled. So radiation resistance will be what? Radiation resistance will be 60 into integration of theta varying from 0 to pi cos of beta L cos theta by 2 minus cos of beta L by 2. Why I am again and again writing is you will get practice of writing divided by sin theta d theta. Okay. This will be your equation 8. Write down. In case of lambda by 2 antenna in order to evaluate equation 8, the help of sin x function and cosine x function is taken. Sin x function and cosine x function is taken. Next, to write a statement. It may be shown that the radiation resistance of lambda by 2 antenna is 30 cosine x function of 2 by pi, which is given as 30 into 2.44, which is approximately 73 ohms. Sorry, C of n is known as the cosine integral. Is the cosine integral. Please write down this. This is your radiation resistance of what antenna? Lambda by 2 antenna. Agreed?
Yes, sir.
Okay, I'll just see in the notes if anything else is there. There are some problems with respect to this. All these problems we have done already, point sources problems. See, this is what I have done today. Radiation resistance of short electric dipole. Radiation resistance of short electric of a short electric dipole. Page 39 of your notes. See, all this I have done. This is what I have put. Then radiation resistance of lambda by 2 dipole. This is what I have done here. See, 1 minute. This derivation of lambda by 2 dipole antenna, what this actually is done by Dr. Venkatesh. It is slightly different from what I have taught you. So you can follow what I have taught you, or if you want to follow this also, no problem. This is being done in slightly different method, wherein the assumptions of your H phi itself has been different. So finally, he is also arriving at the same solution. I am also arriving at the same solution of 73 ohms. I have used here cosine integral. So he has not used cosine integral, but he has done one assumption for this value of H phi. So I'll just show you where is the difference. H phi is just taken as I naught 2 pi r into cos of pi by 2 cos theta sin theta. See, what I have taken here is, where is my H phi? I naught by 2 pi r cos of beta L cos theta by 2 minus cos of beta L by 2. He has ignored this term minus cos of beta L by 2. So if you substitute beta is equal to 2 pi by lambda, then this theta by 2 can be approximated as equal to theta. So then you will get this. If cos theta by 2 is approximated as theta, you will get cos theta here. Suppose this beta is 2 pi by lambda and L is equal to lambda. So what happens is here lambda will get cancelled. So you will get here. So this, sorry, 1 minute. So he has taken cos pi by 2 here. Okay. So pi by 2 he has taken. So the this cos theta by 2 term is and this minus cos beta L by 2 term is neglected. See, what I have done here is the exact definition. What Dr. Venkatesh has done is the approximate definition. So beta is equal to 2 pi by lambda. So what happens? Lambda will get cancelled, and he has done one approximation of here cos pi by 2. So this I naught by 2 pi r, I naught by 2 pi r is a common factor outside. I hope you understood. So with that, he has done some approximation and found the power radiated. I have done with respect to cosine integral. So both the options are correct. Whichever you find it easy, you can do. Got it?
Yes, sir.
Understood?
Yes, sir.
Okay. Please write down one small problem now. I'm not going to rewrite now. You can just take it from there, from this. Write down. A thin dipole antenna is lambda by 10 long. If a thin dipole antenna is lambda by 10 long, and if its loss resistance is 2.5 ohms, find the radiation resistance and efficiency. Find the radiation resistance and efficiency. Okay. Given length of the antenna is lambda by 10, and so loss resistance is 2.5 ohms. Okay, the length is greater than given antenna, that is lambda by 2, which is lesser than. Okay. Okay, so he has taken this formula 80 pi square, that is your short dipole. This is for a thin dipole antenna of lambda by 10 long. So what he has done is 80 pi square L by lambda whole square. Just what we have done for your short dipole. There L you substitute as L by lambda. So if you substitute L by lambda, lambda will get cancelled, and you will get radiation resistance as 7.89 ohms. Have you got it? Just substitute in this 80 pi square L by lambda whole square. In that you substitute L is equal to lambda by 10. So you get radiation resistance as 7.89 ohms. So you get efficiency as radiation resistance divided by radiation resistance plus loss resistance. So you get efficiency as 75.93 ohms. Is it clear?
Yes, sir.
A thin dipole antenna is lambda by 10 long, and its loss resistance is 2.5 ohms. Find this one. So L is nothing but your lambda by 10, and substitute that for your short dipole, this one, and find out this one. Okay. Next question. A magnetic field strength of a 20 microampere per meter is required to be produced at a point 2.5 kilometers from the antenna and in a broadside plane in free space. How much power is transmitted by a Hertzian dipole with L is equal to lambda by 25 meter, a half wave dipole, a monopole quarter wave antenna? This is the question. A magnetic field strength of 20 microampere per meter is required to be produced at a point of 2.5 kilometer from the antenna in the broadside plane in free space. How much power is transmitted by a Hertzian dipole with L is equal to lambda by 25 meter, a half wave dipole, a monopole quarter wave antenna? Okay. Write down. We know that the power transmitted, or this notes is already available, so you don't have to write down. You can just listen here. So power radiated is nothing but I naught by root 2 square, or I naught by 2 into radiation resistance, and H phi is given as 20 milliampere per meter. So 20 into 10 power minus 6 ampere per meter, and your is required at a point of 2.5 kilometer from the antenna. That is nothing but your radius, that is 2.5 into 10 power 3 meter. For a broadside plane, theta is equal to 90 degree. So again use this formula 80 pi square L by lambda whole square your L is nothing but lambda by 25. So substitute here L by lambda by 25 lambda square. So lambda will get cancelled. So you will get 80 pi square 1 by 25 square. That is radiation resistance is 1.2633 ohms. To find the current I naught, it is given as H as 20 milliampere per. What is the value of H5? 20 milliampere. 20. What is that? I just forgot. 20 microampere per meter. Sorry, 20 microampere per meter. So this will be 20 micro ampere per meter. Please write here microampere per meter. For a Hertzian dipole, H5 is given as I naught beta L divided by 4 pi r sin theta. This you already know. This is what we have done in the short dipole derivation. I naught beta L divided by 4 pi r sin theta. Beta is equal to 2 pi by lambda. L is equal to lambda by 25. And r is equal to 2 into 10 power 3 ohms, and theta is equal to 90 degree. So rearrange this equation and get this I naught on the LHS side. So you will get I naught as 2 amperes. So then power radiated is I naught square by 2 into radiation resistance. So you get the power radiated as 2.5266 watts. So you will get the power radiated I naught value and the radiation resistance value for a Hertzian dipole. Hertzian dipole is nothing but a short dipole antenna. Next, the same thing has to be repeated. The same thing has to be repeated for a half wave dipole. Okay. Now, this is the thing here for a half wave dipole antenna where lambda is equal to pi by 2. You have to remember this. H5 you have to take as I naught by 2 pi r cos of beta L by 2 cos theta, beta L by 2 cos theta by 2 sin theta minus cos of beta L by 2. See, this is what we have done here. 1 minute, I'll tell you. This is the general equation, cos of beta L cos theta by 2 minus cos of beta L by 2 divided by sin theta. So instead of doing all this confusion for a half wave monopole antenna, for the problem's sake, you can take cos of theta pi by 2 cos theta by sin theta. You got my point? This is the same equation. So here, instead of beta L, you are having, what is this? Instead of beta L, what is that? Pi by Mahima, what is there instead of beta L? Pi by 2. Are you there?
Yes, sir.
Okay. Are you understanding what I am trying to tell you? These are very important concepts.
Yes, sir.
Okay. Purva Chandra Prakash, are you understanding?
Yes, sir.
Okay. So instead of cos theta by 2, cos theta
Pi by 2.
divided by sin theta. So the whole same thing is put there. So theta is equal to 90 degrees. You will get this value as 1. Then similarly find I naught, that is H5 into 2 pi r. I naught is nothing but H5 into 2 pi r. Then you will get the value of I naught. Find the power radiated I naught square by 2 into radiation resistance. So for a half wave monopole antenna, for a, this is what we have done for a, sorry. For a half wave dipole antenna, for a half wave monopole antenna, sorry, quarter wave monopole antenna, whatever is the power radiated by half wave dipole divided by 2. So your power radiated will be exactly half of that, 1.153 watts. So these are the two problems related to lambda by 2 dipole and half wave monopole antenna. See, this equation is the exact equation. So if you are finding difficulty with this exact equation, because I always do the exact method, so you can also use this equation, which is being used in the notes. So don't get confused. I naught 2 pi r cos of pi by 2 cos theta by sin theta. This is the approximate equation for H5. Okay, this is the exact equation for H5 because this component will be extremely negligible. So these can be neglected. But anyway, I have done with cosine integral. So this is also fine. That is also fine. When you are doing problems, you have to do this approximation. If at all they ask. Okay. So only thing which is left here is, okay, one more question is there. Electric field strength of 10 volts per meter is to be measured from observation point theta is equal to pi by 2, that is 500 kilometer from a half wave dipole antenna operating at 550 megahertz. What is the length of the dipole? Calculate the current that must be fed to the dipole. Find the average power radiated by the antenna. So I'll start. Okay. Given E theta is equal to 10 into 10 power minus 6 volts per meter and theta is equal to 90 degree, radius is 500 kilometer, frequency is 50 megahertz, that is 50 into 10 power 6 hertz. Length of the dipole, given the data, length of the half wave dipole is nothing but lambda by 2. Lambda is nothing but velocity of light by frequency, so c by 2f in this one, so you will get 3 meters. Then the current I0 you find by H5 equating to I0 by 2 pi r cos of pi by 2 cos theta by sin theta. Then you substitute E theta is equal to this much, 10 into 10 power minus 6. We know that E theta by H5 is nothing but 120 by pi. So you get the value of H5 here, and theta is equal to, for theta is equal to pi by 2 for 90 degrees. Assume theta is equal to 90 degrees, you will get as 1. So from that you can find the I0 because you know H5, you can find the I0 value here. Then you can find the power radiated as I square by 2 into radiation resistance. So these are the 3 sets of problems. You can go through that. You want me to do it once again, I can do that. Because of the lack of time, I'm telling to you. So what is left here is only one concept known as thin linear antenna, which I am required to do. Otherwise, your module 4 is completed. One concept of thin linear antenna is there, and one small power theorem is there. So if I do those two, your this one is completed. Module number